In this video, we're going to talk about the set theory basics, symbols, and vocabulary. Because in the overall picture, understanding what the symbols mean and understanding the vocabulary words and how to apply them in the mathematics behind it all is really what it comes down to. First vocab word is set, a collection of objects whose contents can be clearly determined. You use a capital letter to represent a set and brackets to enclose the elements inside the set. So below here we have V equals A-E-I-O-U. So V, that is the set right there. So set V. And equals is just saying like the set V is, or equals. And then A-E-I-O-U is just the contents inside of it. These are, well, I guess we'll find out in the next slide, but they're called the elements. And it's said that these are contained in the set. So elements, the objects in a set. So back to our last slide here, V. The elements in the set are A-E-I-O-U. Set builder notation. So this is a notation that you're going to see a lot, and then I would really suggest getting familiar with it and understanding what it means. So from earlier, the set V is the set of all elements X such that X is a vowel in the English alphabet. So V here you would just pronounce as set V. Equals is pronounced as is. So the parentheses you kind of lead it off with the set of. And where it gets kind of tricky here is the X and then bar and then X, because what this really means is all elements X right here. All elements X. So all elements X, and then this line going up and down here is bar. This is such that. Such that. So all elements X such that X is a vowel in the English alphabet. So pretty much try not to get thrown off by the letter X, because obviously X isn't a vowel in the English alphabet. It's just kind of an arbitrary letter that gets commonly used in place, just so it's like a variable, a general variable. Next is the roster method. That's just listing the elements in the set as you see here. So A-E-I-O-U, just clearly showing what's inside a set. This is really easy if you just have smaller sets, like let's say just some random set S, and what's inside of it would be, let's say 0, 1, 4. That is a set right there. You know, it's pretty easy to list stuff in the roster method. Word description, V is the set of vowels in the English alphabet. That's pretty self-explanatory, just a word description describing it. Well-defined, a set whose contents can be clearly determined. So in this case, we have the set E is the set of all elements X such that X is an even integer, and 1 is less than X is less than 10. I guess that should say even right there, and. So in this, if we want to write this out in the roster method, if it is an even integer and it's between 1 and 10, we'd have 2, 4, 6, 8. And actually, we wouldn't include 10 here because there's no, it's not this less than or equal to. A set that wouldn't be well defined is just something that you really it's not clear what's inside of it. So an example would be the set of lucky numbers. You know, unless it's clearly stated what the set of lucky numbers are, it's just not something that you can just tell someone like, oh, X is the set of lucky numbers. They're not going to know offhand. It's not clearly determined. Empty set, or the null set, is the set containing no elements. So defined by brackets, or these little, these brackets with nothing inside of it. Or also, you can use the phi here, or phi, which is just kind of represents the same exact thing. So these are the same exact thing. This is kind of confusing to get a grip on right away, the empty set, but just kind of get used to the vocabulary, and you're going to see it coming up time and time again later in the chapters. Greek letter epsilon translates to is contained in, and epsilon with a line through it, sure enough, is not contained in. So from earlier, our set V of the vowels in the English alphabet. So U is contained in the set V, and G is not contained in the set V. Cardinality, the number of elements in a set, and cardinal number, the number of distinct elements in a set. So right here is kind of the key takeaway from this. So that you would read this as the cardinality, or the cardinal number of M, it would be 12, and that's the number of months in the year. It's just kind of a way of explaining how many elements are in a set, or distinct elements, I guess. That's important. Equivalent sets, sets containing the same number of distinct elements. So back from earlier, V is the set of all the vowels, so A, E, I, O, U, and some random set R is 1, 4, 6, 9, and 100. These are technically equivalent sets because they have the same number of distinct elements. Now, equal sets are two sets containing the exact same elements. So listed below here, we have A is equal to 1, 1, 2, 2, 2, 3, 4, and B is 4, 3, 2, 1. We can say that sets A and B are equivalent because they contain the exact same elements and same number of distinct elements. If it is good to note too that if two sets are equal, that they're going to be equivalent, because there's no way that you can have because technically these both have 4 distinct elements in them, so they're equivalent too on top of being equal. One-to-one correspondence, which is denoted with this little 1-to-1 here, or you can see 1-1. The elements in two sets can be paired with exactly one element from the other set. A lot of times what comes to mind with one-to-one correspondence is graphing. So like let's say you just had x and then f of x. So if we had some graph that was like y equals 2x plus 1, you just kind of graph a few points, -1 or 2 down here, I guess. So you plug in 2, you're going to get 5, plug in 1, you're going to get 3, 1, -1, you're going to get -1, -3. Or yeah, that's right, I was a little confused myself there. This is a -2. So yeah, I mean that would be one-to-one correspondence because there's a one line drawn from each element in each set. Like if we consider this set and this a set, like x and y. But if you think of a graph like a parabola, we're like, okay, this is our parabola-looking graph. The number, let's say 2, on the graph, let's say y equals x squared. If you plug in 2 and -2, you're going to get 4 and 4 for both of those. So you have the points 2, 4. This point right here is 2, 4, and this point right here is -2, 4. So what this really shows us here is that this wouldn't be a one-to-one correspondence graph because you'd have some set of elements in one spot and a set in another spot, and there'd be more than one line going to one point. So that's where you lose that one-to-one correspondence because exactly one element from the other set is paired with each other. So that's what you really have to look at. And this is kind of a confusing term, and it comes up time and time again, and you really get a greater understanding of it as you progress in your set theory. But that's all for this video. Thanks for listening.